By now you're all probably pretty sick of doing definite integrals, because we have to do all this finding the Riemann sum and then taking a limit, and it's really gross and it takes a long time. Or we have to have a nice accurate graph where we can compute the area directly, and that's just not always possible. So the good news is, today we get to find out how to do those definite integrals without all the awful Riemann sum stuff. Okay, so just as a reminder, when you see a definite integral like this, the integral from a to b of f of t dt, that is a net area. It's the net area between the graph of the function and the horizontal axis, in this case the t-axis, from t equals the lower limit a to t equals the upper limit b. If I replace that b with an x, that's just another variable, I get that this integral, the integral from a to x of f of t dt, is the net area between f of t and the t-axis from t equals a to x. So in a picture, looks like there's f of t, there's a, and there's x, and that's the area. Okay, if it went below the t-axis, it would be a net area, but same idea. But notice that this thing here that I've circled, this definite integral, is a function of x. That is, if you put in a different x value, right, that would move the end point of the area around, then you'll get a different value out for that area. You'll get a different value of the definite integral. So you put in an x value and out pops a number, the area up to x. So that's a function of x. Well, when we have functions of x, sometimes we take their derivatives. So what is the derivative of that function of x? Remember, a derivative is a rate of change. So I'm asking, how is this function changing as you change x? Okay. So here's the picture again. How does this area change, this function change, as x increases? Right? As I move x along, the area in this picture is going to grow. And how much is it going to grow? Well, when I move x over just a little tiny bit, I add a little tiny thin strip over on the right there, whose height is f of x. So the new area I add, divided by the amount x changed, right, the rate of change of area over the change in x, is about that height, f of x. This isn't a proof, but I hope it's a little bit convincing that it is possible to believe that the derivative of the function that adds up area, the accumulation function it's called, which is the integral from a to x of f of t dt, that accumulation function has a derivative that is just f of x. Okay. That is the statement of the fundamental theorem of calculus, part 1. I will abbreviate fundamental theorem of calculus as FTC. So the fundamental theorem of calculus 1 says, if you have a continuous function f, the derivative of the integral is the original function. Okay, that's the simple way to say it. The derivative with respect to x of the definite integral from a to x of f of t dt is f of x. That doesn't seem all that useful at all, but trust me, it is. So we'll see some examples of using it, but the main use will be in allowing us to do the fundamental theorem of calculus part 2, which we'll see in a second. Okay, so the derivative of the definite integral is the original function f. And notice what this is saying is that the derivative with respect to x of an integral that starts at any old number a and goes up to x of this function gives you f of x. So in other words, since its derivative is f of x, that function is an antiderivative of f of x. Right? Its derivative is f of x, so it must be an antiderivative of f of x. Now we know there are lots of antiderivatives for any function. You get them by finding one and then adding constants. So which antiderivative is it? What constant does it have on it? Well, here's what the second fundamental theorem of calculus tells us. You can pick any particular antiderivative you want for your function, and then call it capital F. So capital F of x is any particular antiderivative of little f. Then this accumulation function, this integral from a to x of little f of t dt, is equal to capital F of x, that's the antiderivative, minus capital F of A, that's a constant. So it is a different antiderivative, right? It is the antiderivative capital X minus the constant capital F of A. Right? So it tells you which particular antiderivative the accumulation function is. Again, not tremendously useful until you do this. Replace x with b, and then in that integral on the left, remember we talked about dummy variables, it doesn't matter what variable you use, so replace the dummy variable t with the dummy variable x. And it looks like this. The integral from a to b of f of x dx is capital F of b minus capital F of a. That is, to compute a definite integral, all you need to do is find an antiderivative and plug in the two endpoints of the integration, a and b, and subtract them, which is wonderful. This is a formula that lets you compute definite integrals without having to deal with Riemann sums. Okay, so we're going to look at a couple of examples, one with each part of the fundamental theorem of calculus. So the first one is something that looks horrible, but it's really easy. I want to know the derivative of the integral from 15 to x of 47 times sine to the 8th power of 3 square root of t minus 12 dt. That is, do that integral with respect to t, and then take the derivative with respect to x. And that sounds terrible, except FTC1 said when you do this exact thing, you have an integral from a number up to x of f of t dt, and you take its derivative with respect to x, you just get back little f of x. That's it. So all I need to do is look at the thing I'm integrating and then taking the derivative of. So look at the thing inside the integral. It's got t's in it, replace them with x's, and boom, done. 47 sine to the 8th power of 3 times the square root of x minus 12. That's it. That's the first fundamental theorem of calculus. Here's an example with the second. What is the value of this integral? Now, up till now, we either had to draw a very accurate picture and find an area, or use Riemann sums and take limits, and it was ugly and long. Now it's easy. The second fundamental theorem of calculus says I just need to do capital F of b minus capital F of a. In this case, a and b are 0 and 2. And capital F is just any old antiderivative of 4x squared that I want to pick. Well, my favorite antiderivative of 4x squared is the one where the constant is 0, so 4/3 x cubed. So FTC2 says I just need to plug in 2 and 0 into that and subtract. The value of the definite integral is that antiderivative plug in 2 and 0, and this is the notation that we'll use. It means look at that function, plug in the top number, minus that function, plug in the bottom number. So that function, plug in the 2, minus that function, plug in the 0, and that's 32 over 3. So the value of that integral is 32 over 3 with no Riemann sums in sight. Yay! Okay. We'll do lots more examples in class, and you'll be doing lots more examples for the foreseeable future, frankly, both in this class and next semester. So that's the fundamental theorem of calculus, parts 1 and 2, and I'll see you in class.